Hello, my name is Jang, and this video is going to be a lot different from my other videos. The introduction is going to be way different, but regardless, I still want you to listen, and I'm going to talk about the background of our class and the background of our project within this introduction. So, let me tell you. I am not a hip-hop artist, but in order to be creative, I wanted to do something different. So here's my difference. Let me explain to you the backgrounds of the class and the project. Listen to the words carefully and you will get a grasp of ENME489Y. You ready? I'm ready. Yeah. This course explains the fundamental of remote sensing that includes LiDAR, radar, digital image processing, but specifically we are using LiDAR for the course project as a whole. Students have a semester-long project where we have to build a field deployable LiDAR system that includes a Raspberry Pi with the camera, Arduino and the breadboard with an accelerometer. Also need a power source in order to power up the Pi, but wait, it seems like we're missing something important. That's right, you can't forget the most important part, which is the laser pointer that continuously shoots at our target of our choosing at the University of Maryland. Whoa! Let me tell you something funny. I had an equation coined into my last name by Dr. Mitchell, who calls it the Jang equation. The Jang equation is special, but really the real equation is called the range equation. This equation is the bread and butter of a data collection process. So let me explain what's in it. Range is equal to the speed of light multiplied by the change in time, all of that divided by 2. In short, C delta T divided by 2. It's a little bit of math in there, but don't worry, I'm sure you understood. Now let me tell you what my target is. It's a simple butterfly post that no one ever notices, which is the main reason why I choose it, cause I notice it every second I pass it to go to class. Just recently I got to my target with my deployable LiDAR sensor to scan away until I finished. I never felt so stressed going back and forth reconnecting to the internet to finish up data collection process. I collect the data with OpenCV plus Python, which are both programming languages that you may know, which was to me so confusing cause learning a new language is difficult. But I had to learn it anyways to continue my project, a whole semester long project. In the end, students have to generate a 2D and a 3D plot of the many data processes that you collected inside MATLAB, and in the end, you have to mesh it all together in MeshLab. Now if you want to go further ahead and get bonus credits, you can 3D print it and send it to Dr. Mitchell. So yeah, that's my introduction, talking about the backgrounds of our ENME489Y class and our semester-long project. So basically, in short, if that was too fast, our class explores the fundamentals of remote sensing, which includes LiDAR, radar, and all remote sensing types of aspect. But specifically in our class, we mainly focus on LiDAR, and we use the Raspberry Pi. And in terms of coding language, we don't really learn coding in class, but we used OpenCV plus Python to code, and that is a coding language. But I will explain to you now what my target is and why I chose it here in a few seconds. Alright, so here I am near my target location. You can see my target right there where I'm pointing, but I will explain to you why I chose this target. So if you look over there, right there, that is my parking garage. So every day when I come to school, I park there and I walk down this hill. So the main reason is I don't believe that any other student parks in this garage because one, it's the furthest away from the engineering campus, and two, no one wants to walk a big hill every day when they go to class and coming back to class, or not coming back to class, but going back to their cars. So that's the second reason is, if you see right here, there's a trail path right here. Most students walk down this path when they go to class, and sometimes when they even go back to their cars. Although on the other hand, for me, I walk down the long way. So I'm gonna show you what the long way is. It's a nice, bright, sunny day. A little bit of wind. But yeah, this is the long way. So there's just this bike trail path right here. But regardless, here it is. I'm coming close. I'm approaching my target a lot closer now. This is truly the long way with the big hill you have to climb up, even with curves. But yes, as you can see, this trail right here leads to my garage in a longer way than earlier. But I'm here at my target now, and every day when I take this path, this long way, I see this thing. Third reason is I noticed it. I'm pretty sure that other students do not notice this thing. They don't even look at it. But for me, I have a purpose to look at it. It's my project target. So that's my third reason of why I chose this target. I noticed it. So right here in front of me is my field deployable LiDAR sensing system, and I want to talk about each component that's on this field deployable LiDAR sensing system. So this guy right here, the thing that I'm touching, is called the Raspberry Pi 3, and attached to it is a Raspberry Pi camera module that comes with it. The next thing that I want to talk about is the Arduino, and it's connected to a breadboard with jumper wires, and it has an accelerometer right here. I'm touching it, and this pink thing right here is my power bank. It supplies power to my Raspberry Pi, which supplies power to the Arduino. And the most important thing that's on is my laser pointer. Now this is a green laser pointer, and yeah, this is the most important thing that's on this field deployable LiDAR sensing system. Now my configuration, here it is. So my laser pointer is just roughly a little over 12 inches from my Raspberry Pi camera. So what that means is when the laser is on and you run the code on Raspberry Pi in the terminal window, a video will pop up if you're using a monitor or a TV, and within that video there's crosshairs indicating where your laser pointer should be, your laser spot should be. But in earlier homework we had to make this configuration, like we had to put 12 inches apart from the laser pointer and camera. So when this is 12 inches apart, the closest the Raspberry Pi camera can see the laser spot is 1 feet away. Now that's the very closest it can see because it's 12 inches apart. But as you move further back, that laser spot starting at the right side of the screen, at the right side, and as you move back, it'll get closer and closer to the middle, and then if you go really far back, it'll go all the way to the left side of the screen. So that's coded in the Raspberry Pi under OpenCV plus Python. Now I want to explain the code a little bit. So we weren't given the code, or we were given the code, I'm sorry. We weren't learned or taught how to program in Python. We were just given the code, and within the code there was comments in the code saying if you uncomment some of these lines, then you can save a video. That's the only thing that we had to do in terms of instruction, but we didn't really learn what's going on in the code. Now in one of the homeworks we had to calibrate our Raspberry Pi camera to spot the laser spot. Now in order to do that, the code was running in terms of HSV color space rather than RGB color space. The reason being is in RGB color space, it can only tell you the degree of color. But working in HSV, the hue is the degree of color, whereas the saturation is how much light intensity there is within the color. So it can be very bright, it can be very dark, but the hue will still stay the same. The degree of color will still stay the same. And the value is how much gray you put into that color. And again, the hue will still stay the same, the degree of color. So in terms of the code, we had to manually calibrate to find the green laser spot, and certain students, they had to work at night because their target was green, or their target was really hard to see the laser spot in bright sunny day. And for me, I had to work at night. It was my target was green, unfortunately, but I programmed my Python code so the HSV color space would be in a darker light intensity in terms of the green laser spot. So there were many calibrations that I had to do. Yeah, the first thing was definitely the HSV color space for the laser and the laser spot color. The next calibration was this accelerometer right here. So this accelerometer it tells you what degrees you are in terms of XYZ coordinates. It can tell you where, like, if this is straight right here, this platform right here I'm holding, this is straight, the accelerometer reading will show me 0090, and that means I'm in the 0 degree of X, 0 degree of Y, and 90 degree of Z. So calibrating the accelerometer was a little difficult, not only because when I calibrated it in Arduino code, when I looked at the processing window, it was at 0090, but when I opened the terminal window for the Raspberry Pi, it was not 0090. It was shooting numbers like -4 for X, 2 for Y, and like 85 for the Z. So in order to get a better data and like better sense of like the 0090, the degree, I recalibrated in the Arduino codes to have the terminal window spit out 0090 as this being flat. So that is, this right here is my field deployable LiDAR sensing system and a general background of like what the code is doing and how the camera is finding the laser spot. Alright, so I'm back at my target. My laser pointer is dying, but it's an example of me taking the back side of my target. Laser pointing is still slowly dying, but hopefully I can get something off. I just raise it up slowly, and then as I come up all the way, I go back down. The process is longer than 30 seconds, but it's the best that I can do. Yeah. Right here in front of me is the MATLAB code. Earlier I talked about how far apart my laser pointer is in comparison to my Raspberry Pi camera. So this H right here is the distance. It's in meters, but yeah, that's how far apart. And this MATLAB code is the code we use for our data process after we got the many data points after we scanned. And right here, I just want to show you my new 2D and 3D plot. So here it is. Here's my 2D plot right here, as you can see with my mouse. It's pretty good. I got the data from the front and data from the back. At first it looked like a Y shape, but Dr. Mitchell told me that for the back, I need to turn all my data points around 180 degrees, and I was able to do that. And here's a 3D space right here. And after we processed everything in MATLAB and got a pretty good this data plot, we had to go to MeshLab and create a mesh. And at first my mesh was not good. I didn't really know what it was, but this mesh right here, it looks pretty good. I used a different mesh. I didn't use Poisson's mesh. I don't remember exactly what mesh I used, but this is the mesh right here. It looks pretty good to me. It actually looks like my butterfly post. It's a little it's missing some, I suppose, areas, but it's not connecting it. But to me, it's definitely better than what I had during my presentation. So this is how this is all my data for my project.